Good afternoon. I have some slides which give an overview, I believe, as I'm sitting here listening to these talks, give an overview of a lot of the themes that have been touched on in this session. And I'm going to motivate the whole thing. There is the topic of convergence of HPC. Earlier Professor Panda, DK, talked about the convergence of HPC and big data. I think I'm just using the same word, but I'm saying hyperscale because I'm kind of more from a hardware background. And you can say big data, you can say data centers, you can say hyperscale, Hadoop and all that thing that but convergence of HPC and deep learning is forcing this. That's what I want to emphasize. Let's set the stage. Brian's talk, Julie's talks earlier on deep learning. Let me set the stage by saying that deep learning is nothing less than a new paradigm in programming. The old paradigm in programming was you've got input data, you've got a programmer who writes some code, and those go into the machine runs and gives you an output. Deep learning turns that paradigm on its head, where you give it input data, you give it the sample outputs. You do not write the program. You give it input and output, and you tell it what kind of output to expect. And then the deep learning training sequence spits out the program in the set of in terms of a set of trained weights that runs on this abstract machine, which is a neural network architecture. DNNs are remarkably effective, and that is all the hype around deep learning that you've heard. These are in some ways universal problem solvers, are applicable to a large number of applications, and hence these kind of algorithms are sweeping through hyperscale and data centers. And these algorithms, as we will see, have a lot of requirements which can be satisfied by HPC style computing, but they are now going into the data center, so very significant what is happening for this audience. Training as opposed to compiling. Training is the new compiling. Trained weights as the new binaries. Big neural nets required to process big data. And the words big are often abused, but in this context, I want to assure you that they are not. I'll give you examples of what big neural nets means and what big data means. Of course, everyone here knows, petax are really big data. Videos, images, speech, text, that's kind of classic big data. DNNs are significantly increasing recognition accuracies in a wide varieties of fields where recognition accuracies have stagnated for decades. You can pick a field, pick up your hand, pick a field, and I'll be able to quote you benchmarks where deep learning has just kind of revolutionized the field in terms of this. It is used to structure big data. That's the key. Deep learning is now the de facto tool to structure big data. The neural network development life cycle, you make a guess at a neural network architecture, you train it on a labeled set. That yellow box is the process where you give it your expected output, and what is spit out of that yellow box is the program. You do not write a program to solve a problem. You give the neural network architecture examples of what you want the answers to be, and it figures out the program. Then you test it. Does it perform well? No, you design a bigger network. Does it run? If it runs well, then you run it. Then you need more training data. So these two boxes are what makes it big. When we say big, and let me just give some examples of some numbers. We're talking about 100 million parameters. Somewhere from, the small nets are 20, 25 million parameters. The large nets are 100 million parameters. There are even nets with 1 billion parameters. And we'll get to what the implication of that is. Okay, very good. Earlier I saw one of the presentations which talked about, I think it was DK's presentation, where he said that the utilization on the CPU or on the processor was small, 5-10%. Right. That was when AI was born. Where the CPU is sitting around, it's either waiting on I/O or waiting on some data dependencies or something like this. It has not been able to parallelize effectively, whatever the reason might be. But the CPU was sitting there idle and bigger, and with these very big CPUs that you had, or even accelerators, GPUs and other specialized accelerators, What has happened, these deep neural nets are a fundamentally different kind of compute resource, and let me draw some numbers out here, right? The ratio of compute cycles to I/O bandwidth is significantly higher than non-AI algorithms. If you do a typical web query, what is the address or what is the name of this person, what's the phone number of this person, typically if you look at that end-to-end transaction, then you see the ratio of I/O to compute cycles. How many bytes of input data did I get and how many flops did I do to compute it? It's of the order of 1:10 or 1:100, in that 2 orders of magnitude difference. You look at a deep learning training cycle, and what you see is AlexNet is one of the canonical neural nets, just the most famous neural network in the world, right? And AlexNet for image classification, all these magical image classifiers that you've seen in all the press, 27,000 flops for 1 byte of data. Let me just pause and let that sink in, what that means. 1 byte of data, you do 27,000 operations on it, right? On average, to look over the whole thing. That is why even on the highest end GPUs, and you need weeks, maybe months to train these puppies. So they give magical results. It doesn't come for free. That's the kind of numbers we look at. I like to think about it in terms of the ratio of the surface of a sphere as opposed to the insides of the sphere. The inside of the sphere is the compute cycles. It's the number of states that a neural network can represent. The surface is the I/O bandwidth, right? It's a classic kind of analogy. It's a very good way to think about it. So I talk about the R square R cube volume, significantly higher for deep learning. Power dissipation is an ancillary challenge. Most of what I'm going to be talking about is HPC and in the cloud, so it doesn't matter so much, but this stuff is moving out onto mobile devices as well. And even in the HPC context, and especially in the data center context, we see that power dissipation has become a serious challenge, which this kind of, if you need 100,000 flops to process 1 byte of data, you see that the power density and kind of thermodynamic limits are getting exposed. I think, although I didn't attend all of Brian Catanzaro's presentation, but I think this should be a summary of that presentation. Let me just go through it quickly. Neural networks are breathtakingly simple in the kind of mathematical operations that they do. The small set of nonlinear transform. In fact, 5 years ago, if you looked at the set of nonlinear transforms that the neural networks were doing, there were maybe a dozen or so, and you had to implement them using lookup tables and stuff like this. Today, there is 1 or 2, so it's kind of converging. Small set. Small set of linear algebra primitives. If you can do a vector sum, if you can multiply matrices and invert them, you're done. You've got the basic compute primitives to support deep learning. A relatively modest dynamic range of weight and data values. I really want to stress on this one because there's a lot of talk about 64-bit stuff, especially in the HPC community. That is one of the places where there is friction, because every HPC benchmark that we look at is 64-bit benchmarks and 128-bit benchmarks, matrix multiply and all these linpack sort of stuff, which you folks are very familiar with. Please, my message here is that deep learning needs 16 bits. Needs 8 bits, 16 bits, 32 bits. We do not need 64 bits. So please give us what you do, but with lower precision. Because the dynamic range of weight and data values is relatively modest. Very regular repetitive data flows. The only persistent memory requirement is for weights. So, there was the chart of the picojoules of how much it takes to move it from, register to processor, memory to processor, DRAM to processor, RAID or SSD to processor, and you can see it's order of magnitude going up. Good news, bad news over here is that the only persistent memory requirement is this. The big challenge is right here. I said that was breathtakingly simple, and those points pretty much summarize, what a deep neural net does. Variance in the size of the net across applications is very large, 5 orders of magnitude. Let that sink in, right? The smallest neural net to the largest neural net, very same application, but you give it more and more data as the reality it is trying to model becomes more complex. You go to bigger and bigger neural nets. So the challenge is to support seamlessly this very wide range of size of data and their applications. A word of kind of a thanks to Andrew Ng. That is why Minds.ai is the company I work for. And it was Andrew Ng who, almost 4 years ago now, 2008, he first started doing this right here at Stanford. Brian Catanzaro now works with Andrew. And that was what got us started. Because Andrew Ng, for years at this point, has been saying, deep learning folks, please work with the HPC folks, and HPC folks, please work with deep learning folks, right? Because deep learning is the one application which all of you folks should be very excited about, right? Because right away, your markets and all the kind of the verticals you're tackling, they explode, right? Your markets explode with deep learning. That's what we started doing, and I'm going to talk about it, kind of neural network design expertise, HPC, our company, we bring these two together, right? And we focus on image and video recognition, but that's almost besides the point. The rest of this talk, I'm going to talk about parallelization and heterogeneity, and right there, I'll pick up from the last talk where it was that the parallelization is going to give you that last bit of Moore's law, right? Because now where we are at, you're not getting orders of magnitude from just making transistors run faster or build denser chips. Where you're getting it from and what the GPUs have demonstrated very effectively to the whole world is that you have a whole bunch of parallel processors which are quite simple, right, which have a RISC-like instruction set, a small set of instructions. Remember I said, right, that video processing, deep neural nets, all these applications which GPUs are good for, they have a small set of linear algebra primitives, right, but massively parallel, right? So simple operations run many, many times, on kind of vector-like operations. So 7 levels of parallelism. I'm going to look at the stack, which has become very familiar to you folks over the course of these 2 days, and I'm going to look at it from the deep learning point of view. Instruction level, that was covered a lot in this RISC architecture. I'll get to some of those. Thread level, processor level, right? This is the realm of multi-core, of Knight's Landing and GPUs and all this kind of processors. You go higher up the stack, and you've got server level, many GPUs in one server, right? Cluster level, many servers with a high bandwidth, InfiniBand sort of interconnect. And the fun part starts in data center and planet level. I'm giving another talk in a month where I talk about planet scale computing. That's that 10 power 5 variation we are talking about. I'll go quickly over the slide, but those are the various levels of the verticals. You have the ASICs, the CPUs, the GPUs, the FPGAs, and the switch fabrics. You have appliances, you have drivers. On top of that, you have the various primitives. You have the cloud middleware to access all the data. That was the other talk today. And right at the top, you have the neural network designer who's using this entire kind of HPC stack. And you can see it's a nice mix and match of technologies which has come out of the data center, stuff like Hadoop linked over Ethernet and slow systems, slow wimpy nodes, as I like to call them, right? Distributed, connected slow nodes. And a lot of these, the bottom half of the stack is HPC. So look at what is happening here. This is what our product looks like, right? The top, you've got data center-like stuff. The bottom, you've got HPC-like stuff. And you have to put those two together to solve this problem. That is the good news. Okay, I'll go over the ASICs quickly because it was a lot of the stuff that I would have talked about on this slide it was in the previous section. I want to talk about Denardian scaling though. How many people here know what Denardian scaling is? Okay, just a quick introduction. There is talk about Moore's law breaking down, right? I'm here to say that is not true. Moore's law in its entirety is not breaking down. Half of Moore's law is breaking down. What does that mean? You can keep sticking in more transistors. Transistors are getting smaller. You can still keep doubling the number of transistors. What you cannot do is dissipate all the heat that those transistors generate, because in the era of post-Denardian scaling, I think I've got a slide. There you go. The one thing to point out here is that the VDD, the supply voltage, is not going down. We have all lived and grown up in the age when VDD has gone from 5 volts down to 1 volt, 0.9, even 0.7. It's over. Transistors are getting smaller. VDD is not going down anymore. There are some very fancy techniques which, semiconductor companies are working on. But the point here is You can get more transistors into silicon. You cannot run them all together. So my claim is that heterogeneity in enterprise silicon is what's going to win the day. That multi-core and kind of parallelization, in the style of GPUs, NVIDIA has demonstrated and completely convinced the world, but all those cores look identical, right? So as we move along and as the GPUs go to smaller and smaller process geometries, they will be able to have many cores. You will not be able to clock them all together, right? So I believe that where the innovation will come from is from heterogeneity. You will put different kinds of cores and you will use them for different tasks, and you would time cycle between them. So the whole chip does not light up at the same time. Lots of specialized silicon, HPC, that's where HPC kind of coming into the data centers. Let's go to the next level of parallelism, which is the server level and the cluster level parallelism, right? This is right, we are right in the HPC domain at this point. So that's the claim. Deep learning is driving the convergence of high-performance compute and hyperscale. Traditional HPC ecosystems are high-performance, expensive, and bleeding edge. We know that, right? Traditional data structure infrastructure is cheap, robust, and redundant. They throw a lot of cheap hardware. CPUs and Ethernet, right? 10 gig Ethernet still proliferates, right? All over the place. And the server, a typical server, what the industry calls a pizza box in the data center, was like, a typical CPU, one or two socketed, with maybe one accelerator, a GPU or something like that. Even that is rare, right? Typical pizza boxes, about 100 watts dissipation, this kind of thing. All of kind of the cloud and social media and everything that has changed our life is built out of that. Ethernet, CPUs, cheap, robust infrastructure. All of that is changing. Changing, if you believe the deep learning promise. GPUs are very common in data centers, right? There was initial resistance. There was initial resistance because they were expensive, because they burned too much power. But again, back to my hero, Andrew Ng. Andrew and his lab at Stanford, they demonstrated very effectively what you could do with a very few GPUs. You could hook together in an HPC-like cluster. You could rival the performance of 10 times as many CPU cores, right? So he showed that trying to keep the data center cheap, the infrastructure cheap, and resisting HPC-like equipment was being penny wise, pound foolish. Let me repeat. Andrew Ng with deep learning demonstrated that if you buy higher end equipment, you can actually save money given the kind of applications that are coming. So with that, you see that now, a lot of data center companies show up at the GTC, at NVIDIA's, GPU Tech Conference, because, that is the tipping point has been reached, I believe. GPUs, InfiniBand, those are the very good examples. Dense compute clusters require high bandwidth interconnects, right? Server architectures. One point to note here is that if you can tightly couple the accelerators inside a server, and by tight coupling I mean high bandwidth, low latency connections, then this trend will push towards bigger and bigger servers in the data centers. On the other hand, if the InfiniBand, the bandwidth between servers, that speed, that bandwidth and that latency kind of goes faster, then that will push the data centers towards smaller servers and more distributed servers, right? So this is a very interesting, right now what we are building, what the deep learning community seems to have settled on is about 4 to 8 GPUs per server, right? And you want to scale beyond that, then you go to like a multi-server software stack with MPI and all that good stuff to communicate between them. So we believe that data centers will get full of these kind of HPC-like clusters. About 40%, I've seen the estimates, which is a very large number if you look at what hyperscale is today. It will coexist with CPU-based servers for search and database operations, the old stuff, right? Many kinds of servers, one size fit all does not work. So heterogeneity and parallelism, those are the themes of my talk. This is what one of those servers looks like. If you look at at the Big Sur standard that Facebook has released for deep learning. That looks pretty similar to this. You will see a lot of kind of high performance HPC server vendors beginning to put out things, two groups of GPUs, either sitting on two CPUs or sitting on one CPU. There are lots of pros and cons to how this thing is hooked up, but that's what a server now looks like. Before, it used to be 1 or 2 CPUs and 1 or 2 GPUs, right? And look at how dramatically different this is, right? A GPU at this point, the highest end GPUs can do, 6, 7 teraflops kind of thing if at full utilization. This thing has got 6 multiplied by 8. That's 48 teraflops in one server, right? Let that sink in. And my claim is this is going to get commoditized. 20, 30 teraflops in one server and a data center full of 30,000 such servers. That is what the future looks like, hooked together by InfiniBand. This is one of our racks that we deploy in a data center to run deep learning training algorithms. So the previous slide I showed the servers. We have 1, 2, 3, 7 servers in this. So that's about 50 GPUs. And there is one for RAID access. There are one Ethernet switch for the control plane, one InfiniBand 100 gig, high-end Mellanox InfiniBand switch. Just look at some numbers, very startling numbers, right? 8 GPUs per node, 2.5 kilowatts per server node. That's a large number, right? 2.5 kilowatts, For a while, I had one of these things in my house, and I didn't have to turn on the heat, seriously. Okay, I've got 3 minutes, and let's talk about data centers architectures, right? So people are beginning to talk in terms of computing superclusters. Now, computing supercluster is a term very familiar to anyone who's worked on a supercomputer. But there were a handful of supercomputers in the world with very smart people who required multiple PhDs to program these things, and large teams, right? We have a bunch of those supercomputer programmers working in our company. What is happening is the commoditization of the supercomputer. Supercomputer is a cliche term, so I like to use the word superclusters. These are large, large farms of these, 20, 30 teraflop servers. Large number of co-located servers running the same job. High bandwidth, low latency interconnect, we know all about that. Such clusters could grow to be a significant fraction of the data center. This point is very important. Architecture of clusters will be hierarchical and heterogeneous, right? Not homogeneous. There is massive levels of parallelism to be exploited, and hierarchical, right? The very structure of these neural nets are hierarchical, meaning the lower levels will perform kind of utility functions. As you go to higher and higher levels, they will become more less I/O and more compute, and they will be drawing insights. They will be crunching neural nets and stuff like this. We've got some examples where. We're very close to publishing a couple of white papers which will show examples of what those hierarchical heterogeneous kind of clusters will look like. I've got some bullet points over here, right, to kind of motivate why this will happen. Edge servers will be different. There will, for example, neural nets which are classifying, which are looking at videos and classifying for security, not safe for work, content filtering, stuff which is not looking at text, which is not looking at metadata, but is looking at the content itself and deriving meaning from the content. Just like if you were to look at a video, you would be able to classify it. Is this an advertisement? Is this porn? Is this work? Is this a technical talk, right? Deep neural nets can do that. They can actually look at the video and make this sort of classification. So this sort of neural nets will be running on the edges of the cloud. Dedicated RAID servers, which is on the training side, dedicated compute servers. As you see in our example, we've got servers which are dedicated RAID servers which are dedicated compute servers, and that's the notion of heterogeneity. And then control and management nodes. Of course, this virtualization, containerization stuff that we have talked about, dedicated servers to do that. That's this point. multi-DC training clusters for big models are technically feasible. This community, I don't have to sell it to, that the scientific community has performed transcontinental simulations, right? There have been examples of multiple data centers running the same compute jobs, right? That's the future. That's more and more of that is going to happen. And that's perfect. I've got 11 seconds. Okay, very good. Questions, comments?
Well, you mentioned basically vertical versus horizontal scale in terms of compute density and heat dissipation. You didn't mention the size of failure domains, although you did mention bandwidth and latency. But is the size of failure domains a consideration as well as in terms of whether you're going to scale nodes vertically or scale up horizontally?
It's a good question. It's a good question. There are, I don't know what the right answer is. I can tell you my opinions and tell you what we are seeing in the industry. Again, I'll answer the question from the deep learning point of view. There are there is stochastic gradient descent is one of the most favorite techniques to do these training. That is a stochastic process by its name, and hence what that means is if you've got 100 nodes working on the same job, if a couple of nodes go down, because the process is stochastic, it's okay. You do not, one node going down does not kill the whole job. There are other approaches to deep learning which are more synchronized and less stochastic. In those approaches, you would have to take care of multiple levels of redundancy and robustness and kind of failure tolerance mechanisms. I guess what I'm saying is there is an algorithmic way to deal with this, and there is a infrastructure way to deal with this, right? So if you have redundant infrastructure, right, highly redundant infrastructure, then you might pick a sort of algorithms. On the other hand, what we have done is we have picked redundant algorithms where we can really, work on be a little bit hardware agnostic and not require such high robustness. Am I answering your question?
Oh, absolutely. Yeah, it depends.
It depends. There are both approaches. Very greenfield, right? Very greenfield. Let's see how it comes out. In my experience, what I've seen with bleeding edge technologies moving into industry, if there is an algorithmic way to handle redundancy and robustness, then that is always the preferred approach. So we are definitely betting on that. But this is a controversial question. That's why it's a good question. So our company, we are betting on non-redundant hardware, and we'll take care of it at the algorithm level, right? That's our bet. Okay, very good. Thank you.